So, welcome to Fluid Dynamics, MA4002, Tutorial 2. Yeah, we shall get started with this tutorial. So what is this tutorial about? This tutorial is mostly about isentropic flow. Isentropic flow. Okay, so yeah, let's get started. So, we are going to use this set of formulas here, and I think I'm going to create two versions of this tutorial. One using this formula, and another using the tables. Okay, so let's start with using the formula first. In a separate video, in a separate set of videos, I'll show you how to use the table. Okay, so that everybody knows how to use whatever techniques. Okay, so let's get started. Air is extracted through a nozzle from a large tank in which the temperature and pressure are 70 degrees Celsius and 101 kPa absolute value, respectively. At one location in the nozzle, the static pressure is 25 kPa, then the diameter is 15 cm. What is the mass flow rate if the flow is assumed to be isentropic? Okay, so the hint here is the velocity of the air in the tank is negligible. Hence, the conditions in the tank are considered stagnation conditions. Okay, so what they mean is what you see here, this temperature and this pressure, they will be your P naught and P naught. Okay, so naught, okay, naught here denotes stagnation, okay, stagnation conditions. So T naught means your stagnation temperature, P naught means your stagnation pressure. Okay, but degrees Celsius is not a very useful temperature unit here. Okay, so whenever you see temperature, please change it to kelvins. Okay, it's almost never useful to have it in degrees Celsius. Okay, so 70 degrees Celsius in kelvins is 343, and how do I do that? I get 70 plus 273. Okay, and P naught is 101 kPa. Okay, we can just leave it as kilo pascals. We don't need to change it to pascals for now. Okay, I'll tell you when to change it to pascals. Okay, and then at one point, at one location, the static pressure is this. So we can call this point one. Okay, we just give this point a name. Okay, so we call this location point one, and then accordingly, its pressure would be P1. Okay, so P1 equals to 25 kPa, and the diameter here is D1. Okay, so what's useful about the diameter? I'll just tell you that straight up, it will give you your cross-section area. So D1 will give you A1. Okay, so they ask for mass flow rate. So let's get started. Okay, let me just something over here. Okay, so yeah, I don't know why my OneNote just crashed. Hold on. Wait. Uh, yeah. So let me just copy this down here. Okay, so anyways, let's get started. So a good habit to do is to draw out this problem, okay? Draw out this problem. So we start out from a large tank, right? So this is gonna be my large tank, okay? This is the stagnation point, okay, of the large tank. And then this is some flow, and it goes down to a point we label as point one, okay? And then the conditions that they provide for us, okay, so this is point zero, which indicates the local isentropic stagnation condition. So this is T naught is equal to 343 Kelvin. P naught is equals to 101 kPa. And then here P1 is said to be 25 kPa. And then V1 is 101. But then this will give us information on the cross-section area, which is given by pi d squared over 4, which is this, pi d squared over 4. Okay? So our mission here is to find m dot. Okay? So mass flow rate, right? All of us know that mass flow rate is given by uh, density times volume flow rate, and volume flow rate is given by area times velocity. Okay, so we will use 0.1 to calculate the mass flow rate. We cannot use 0.0, right? Because the velocity here is 0, right? So if the velocity here is 0, then the mass flow rate is 0, okay? So it's not a useful point to consider. So yeah, we shall use 0.1. Having said that, this density will be ρ1, this area will be A1, and this velocity will be V1. Okay, so we're using the properties of 0.1 to calculate the we're using the properties at 0.1 to calculate the mass flow rate. Right? So do we know these values? We know A1, okay? A1 is given by this. Do we know ρ1 and V1? No, right? We don't know what's ρ1 and we don't know what's V1. But can we find them? Yes. Okay, so let's do the easy thing first. The easy thing to calculate is V1. And how do you find velocity? You usually find it using Mach number. Okay, so Mach number's definition is V over C, right? In this case, we're considering 0.1, so it'll be M1 equals to V1 over C1. Okay, so how do we find V1, right? If we want to find V1, we need to know C1 and M1. Do we know these two values? And for now, no. Okay, so we don't know what's this and we don't know what's this. So we need to find them. So can we find Mach number of 0.1? And the answer is yes. How? You see, we had the pressure at 0.1, and we also had the pressure at the stagnation state. Okay? This is useful. If you have the pressure at a point and its corresponding stagnation state, right? This will unlock for you the Mach number. Okay, so let me show you how. So let's go back to the formulas that we seen up here. Do you see this formula? We're gonna apply this one. Okay, so let me copy it down. So the formula states P naught over P is equal to 1 plus K1 over 2 M, sorry, M squared. Okay, because we are applying this to 0.1, so the subscript here are put as P1 and M1. Okay, so if you're instead applying this to M2, then this will be P2, M2. If you're instead applying this to a 0.3, you call this P3, M3. Okay, so I hope you understand my point. Okay, so we're applying this to 0.1, so put this at 1 and 1. Now we shall substitute with whatever we have. See, we know P0 as this, P1 is this, so let's substitute those values in. So 101 kPa, 25 kPa equals to 1 plus, okay, so for air, K is 1.1, 1.4, okay, 1.4. M1 is the unknown we want to find. Okay, so you see, M1 is our only unknown, right? So kPa can cancel. See, that's why you don't need to change it to Pascal because the kPa's will just cancel out. Okay, so how to find M1? Well, you can use algebra, but I can show you how to use a calculator instead. Actually, you can just use algebra. It's quite simple. But more difficult formulas will require your calculator. So let me just show you. Okay. So, oh, I should be using it. Oops, I want a graph. Yeah, add graphs. Okay. So on the left-hand side of the equation, we have 101 over 25, right? On the right-hand side, we have the bracket. So what you need to do is bring the right-hand side over to the left-hand side. So what would that become? It will become minus that entire bracket. So 1 plus 1.4 minus 1 divided by 2 times, the unknown is the Mach number, right? So x squared to the power of 1.4 divided by 1.4 minus 1. Okay? Yeah. So you see, essentially here, this is the left-hand side, minus away the right-hand side. Okay? So you enter that, and what you get is this graph. So where is the Mach number? The Mach number is given by the roots of this graph. So we want to find the roots, which means find a zero. So find a zero. It'll be this one. Okay? 1.57. You might ask me, well, what about this root, right? You see, it will obviously not be that root, right? Because this root is a negative value. There's no such thing as negative Mach number, okay? Mach number is 0 and above, okay? 0 and above. No such thing as negative Mach number, so it cannot be this root. Okay, so yeah. So according to our graph here, it's 1.57. Okay, so 1.57. Okay, just keep in mind that this is the Mach number. Okay, it's you don't have to do this, but it's a good habit to identify what what type of flow is this. So what I mean is this one is a supersonic flow. Supersonic. Okay, because this value is above 1. Mach number above 1 is supersonic. Okay, so we already managed to find M1. Now we need to find C1. Okay, so how do we find C1? Okay, it's very simple. C1, hold on. Okay, C1 is given by the formula. C1 is equal to square root of KRT1. Okay, so we know K, we know R, we just need to find T, right? We need to find T because that's the unknown right now. So let's go back up. Yeah, we do not have the temperature at 1, but we can find the temperature at 1. How? See, you have the stagnation temperature, right? And then you have the Mach number. That will help you find the value of T1. How? You use the formula up here. So we're going to use this formula now. So let's copy that down and apply it to point 1. So the formula states that T naught over T is equal to 1 plus K minus 1 over 2 m squared. So let me see if I write this up. Yeah. So because we're applying this to point 1, you label here T1 and M1. Okay, so now let's fill up all the fill up the variables that we know. We are told that stagnation temperature is 343. This one is unknown. Then this is 1.4 minus 1. Then M1, right? We already found this now, 1.57 squared. Okay, so what am I talking about? I'm talking about this M1 here. Okay, we found that just now. And that's why the main idea behind compressible flow, right, is always to calculate Mach number. Mach number will help you access many, many values. So as a rule of thumb, right, for compressible flow questions, the go-to thing to do is always to find Mach number. Okay, keep that in mind. It's always to find Mach number because Mach number will help you access the other values, whether it's the stagnation values or whether it's the static conditions. Okay, static conditions means T1, P1 or T2, P2, for example. Okay, so you see T1 is our only unknown. So T1, you can calculate it to be 230.1 Kelvin. Okay, so with this static temperature at point 1, we can find C1. So C1, remember, is KRT1, right? So KRT1. Okay, so the speed of sound will be 304.1, yeah, meters per second. Okay, so finally we can find velocity at point 1, right? So velocity at point 1 is given by m1 times c1. Okay, so m1 is given by, the Mach number we found just now, times c1, which is this one, 304.1. So this will give you a value of 476.1. Okay, so this is our flow velocity at point 1. So remember, don't forget, we want to find this, right? So let's check what we have already. We have area, we have velocity, we still don't have density. So how do you find density? It's very simple. What you need to use the uh, ideal gas equation, okay, the ideal gas law or the ideal gas equation. So P is equal to rho R T. Because you're applying this to point 1, is P1, rho 1, and T1. Okay? If you rearrange this, it'll be rho 1 equals to P1 over R T1. By the way, this is also called equation of state. Okay? Equation of state. Otherwise known as the ideal gas law. Okay? It has two names, equation of state or ideal gas law. Okay, then you sub in whatever you know. Yeah, and we already know that this pressure, right, is 25 kilopascals. That's given in the question. But here you don't use kilopascal, you use pascals. Okay, this one has to be SI units. So kilo means 1,000. And then R is always 287. Temperature, okay, temperature we already found, right? When we are finding the speed of sound, we found this temperature, 230 Kelvin. Okay, so you found your density. You will find that your density is 0.378. Finally, we can find the mass flow rate, right? Because we have density, area, and velocity. Okay, so sub in your density. Then your cross-section area is the pi d squared over 4. And finally, your velocity was the 476.1 that we found just now. Okay, if you do that, you end up with 3.18. Yeah, 3.18 kilograms per second. Okay, so they didn't ask this, but here's an additional question to consider, which I guess is very important. Additional question. Can you predict the shape of the nozzle based on what you found? Okay, based on the values that you calculated, you should be able to correctly infer what is the shape of the nozzle. Okay, so let us take a look at this flow process from the diagram that we sketched. You see, we started from the stagnation point, right? Okay, this is important to know that it's a stagnation point. Why? Because by definition, stagnation point means the point at zero velocity. Okay, so remember that Mach number is given by V over C. If V is 0, then Mach number is 0. Okay, if Mach number is 0, right? See, Mach number less than 1 is subsonic. Okay, so at first, it was at a subsonic state. Okay, look at point 1. Remember that we calculated earlier that point 1 has a Mach number of 1.57. Okay, what is this? This is supersonic because Mach number is above 1. So what I want you to understand is that we went from subsonic to supersonic. Okay, we went from subsonic to supersonic. Why is that important? It's because this shows that Mach number is increasing. Okay, in other words, we are accelerating the flow. Okay, we are accelerating the flow. At some point along this flow, right, Mach number must reach 1. Okay, because you see this is 1.57 and this is 0. So somewhere in between must be Mach number equals to 1. Okay, so why is that important to know? Because in this region, when Mach number is less than 1, this is subsonic, right? Subsonic. And because the Mach number is increasing, okay, Mach number is increasing means this is an acceleration. So this is subsonic acceleration. What about this other side here? Here, Mach number is above 1. So this is supersonic. But then Mach number is also increasing. So this is a acceleration. So you see, in this whole process, we have a subsonic acceleration followed by supersonic acceleration. So how do you accelerate subsonic flow? You accelerate a subsonic flow using a converging nozzle. Converging. Okay. Then supersonic flow, you how do you accelerate a supersonic flow? It's counterintuitive, okay? So in the supersonic regime, the how the nozzle varies, the nozzle area varies in order to create acceleration is counterintuitive. So this should be diverging. Okay, it's a diverging nozzle. That's how you make supersonic flow accelerate. It's using a diverging nozzle. So you see, it's counterintuitive. Our intuition tells us, right? Okay, based on what we know, for example, normal incompressible water, if you lower the cross-section area of the pipe, the flow speed should be faster. Okay, that's our intuition, right? So let me tell you what I mean. Q equals to A V. If I make V the subject, Q over A. Okay, for a constant flow rate, if I drop the area, then the V should increase. If I increase the area, then the V should decrease. This is intuitive. This is what we know in real life. But supersonic flow is counterintuitive. Okay, so it does the opposite thing. Okay, yeah. So expanding area will make it faster. Contracting area will make supersonic flow slower. Okay, so it's counterintuitive. Yeah. So you see, it is the nozzle has to converge at first and diverge later. So you can tell that the shape of the nozzle must be uh converging, diverging nozzle. Okay? Yeah. So this is how you logically uh find out the shape of the nozzle. Okay, let's move on to the next question. Wait, excuse me first. Okay, question 2. At a section in the channel, an airflow has the following conditions. Okay, so we have the pressure, temperature, and speed. Okay, so let's call this point 1. Okay, so this will be P1. Okay, this is temperature in degrees Celsius, but change it to Kelvin. So plus 273, you have 283 Kelvin. Hold on. Yeah. Okay, so this will be T1. This is V1. Assuming that the flow is isentropic, determine the Mach number at the point where the pressure is this. So this is P2. Okay, we will call this point 2. Then sketch the shape of the channel and explain. Okay, so the mission is to find M2. Okay, so let's sketch out this flow. So we have point 1, followed by point 2. At point 1, we are told that the pressure is 150. Temperature is 283. Velocity is 120. Okay, pressure is 50 kPa. And then the Mach number is unknown. Okay, so how do we go about finding M2? Well, here's the trick. You see, this time we are not given any stagnation state, right? We're given 2 points along the flow, but not the stagnation state. But the main feature of this flow is that it is isentropic. Okay, that's important to know. Isentropic. So what is the special feature about an isentropic flow? here's the thing that you have to note. Okay. So for isentropic flow, stagnation conditions are constant. Or in other words, you could say it's shared. Okay. Throughout the flow. Throughout the isentropic flow. So what does that mean? Meaning to say that the P naught for 0.1, right, is equal to the P naught for 0.2. Likewise, okay, the T naught for 0.1 is equal to the T naught for 0.2. Okay, what else? The rho naught for 0.1 is equal to the rho naught for 0.2. So this is what I mean by the stagnation conditions are shared. Yeah, the stagnation conditions, the T naught, P naught, rho naught, whatever naught, for 0.1 is exactly the same for 0.2. Okay, so that is a special feature about isentropic flow. You need to know this. Okay, you need to know this. This is a fundamental property of isentropic flow. Okay, so that's how you solve isentropic flow questions, is to know and digest this fact that stagnation conditions are shared between 2 points in an isentropic flow. Right? So this is important to know. Okay, very, 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 very important. So please, please, please remember this fact. Okay? Having said that, okay, what we can do is we find the our aim is to find the stagnation pressure. Okay, let's find the stagnation pressure. But to do that, right, remember we always need the Mach number first. So that's what you always do in compressible flow questions. Find the Mach number wherever you can. So let's try to find the Mach number for 0.1. Mach number by definition is V1 over C1. Okay, so V1 is given. C1 can be found using square root of KR T1, right? So V1, they told us 120. Here, K, R, T1 is 283, right? I'm referring to, yeah. Okay, so if you calculate this, your Mach number will be 0.3555863. So again, it's a good habit to label what type of flow this is. And this is subsonic flow because it's below 1. Okay, so now, this formula up here, right? So I'm referring to this pressure formula. We will apply that. Okay, we will apply that to find the stagnation pressure. Okay, so the formula states P naught over P1 is equal to 1 plus K minus 1 over 2 M1 squared K over K. Okay, I mean, of course, you can straight away sub in the values, but I'm trying to be thorough here so that you understand what I'm doing. So P naught over P1. P1 they told us is 150 kPa. Then for air, K is 1.4. M1 is the value we found just now, 3.55863 squared. Okay, so just FYI, the Mach number is from here. You calculate your rho naught, it'll be 163.7 kPa. Okay, so this is useful because the points 1 and 2 share the P naught, right? So what I mean is P naught for 0.1 is equal to P naught for 0.2. And since we know the stagnation pressure and the static pressure at 0.2, this will help us find the Mach number. Okay. Yeah, so this will help. Having P2 and P naught will help us find the Mach number. How? You just use this formula again. Okay, so just use this formula again, but you apply it now to 0.2. Right? So P naught over P2. Okay, now I'm going to straight away sub in the values. So we know that P naught is this one, 163.7 kPa. Over P2, they told us 50 kPa. Okay, and then you apply that formula that you saw just now, 1 plus 1.4 minus 1 over 2. M2 is unknown, so you just leave it as it is. Okay, so now M2 is our unknown. So what we can do is we use our, okay, you can solve this algebraically, but I'm going to show you how to use your calculator to find this. Okay, so let's open a new document. Okay, so we want the graphs, right? So the left-hand side, okay, the left-hand side shows 163.7 divided by 50. And then the right-hand side shows that bracket, right? So what you do is just move it over and then minus away that bracket, 1 plus 1.4 minus 1 divided by 2 x squared to the power of 1.4 divided by 1.4 minus 1. Okay, so again, you take the positive root because there's no such thing as negative Mach number. So you take the 0, and this is about 1.42. Okay, so that's how you get the Mach number using your calculator. So let me go back to my OneNote. Okay, so the Mach number we found is 1.42, and this is supersonic. Okay, because it's above 1. Okay, so yeah, that's how you find the Mach number, which is what they want, right? Yeah, they ask for a Mach number, and now they ask for the shape of this. So now that we know that this is 1.42, okay, we can investigate what shape is required to uh, allow this kind of flow. So remember, Mach number at point 1 is 0.355. Okay, so Mach number is 0.355. So let's take a look. At point 1, because Mach number is below 1, this is subsonic. At point 2, this is supersonic. So you see, you're accelerating, right? Because you go from 0.355 to an increase up to 1.42. So the flow velocity increases, meaning this whole thing is an acceleration. Somewhere in the middle must have a Mach number of 1, right? Because 1 is between 0.355 and 1.42. So somewhere in the middle must be Mach number equals to 1. So here, in this flow, this will be subsonic acceleration, and the rest of the flow will be supersonic acceleration. Super acceleration. To achieve subsonic acceleration, you need a decreasing cross-section area, which means this is a converging channel. Converging. Whereas for supersonic acceleration, okay, it's counterintuitive. So instead of restricting the flow area, you need to expand it. Okay, so this will be diverging. So at the end of the day, collectively, together, this will be a converging, diverging nozzle. Okay, so the answer is the shape. Okay, they asked us to sketch the shape. So, okay, like that. So this is a converging, diverging nozzle. And because it passes through the sonic flow, right? So meaning is that m equals to 1. The sonic flow must necessarily be at the throat of the nozzle. Okay, so this is the point where m equals to 1. In other words, we call this the critical point. Okay, the critical point, which we denote with an asterisk or a star. Okay, so that's how you do question 2. Okay, so I'm going to stop the video here and continue the rest of the questions in separate videos.